Welcome here at the TU Delft in our laboratory, Stephen 2. The integration of LDV is really important to understand how the system works, and for the system you need partners, you need stakeholders, you need everyone to make it happen. Therefore, me as a director of Delft Rail here at the university, we work all together to make it happen. And you can say, how does it look like with the LDV connected to the real world? The LDV is really the connector to find the system approach to make things happening. And does it work? Yes, it works.
We here now introduce a license of the vibrometer to measure railway track vibration from operational trains. This you can do the measurement in one go, for instance, for the whole network. This is a license of the vibrometer. You show the LDV, so you see the laser comes here and then look at the rail. The laser point to the surface of the places where you want to measure the vibration, because the vibration itself has a velocity. This velocity changes the frequency contents of the reflected laser beam. So by comparing the original frequency and then the reflected laser's frequency, then we can measure the vibration velocity. So for instance, in TU Delft, we are putting LDV in trains. When the train moves, for instance, in a normal operation, then the LDV scans the railway infrastructure, for instance, the rail, or it can be the sleepers, the ballast, the embankment, the slat, whatever you want to measure vibration of. By doing this, then you measure the vibration in one go.
So with information we are collecting from the train-borne LDV combined with AVA, we obtain relationships of the dynamic responses of the railway track. Traditionally, such a sort of information was obtained with hammer test. Basically now we are able to perform a hammer test wherever we want, on the run, using passenger trains. Finally, this kind of dynamic information is super useful for optimizing and deciding on prescriptive maintenance, because then this provides a more broad and detailed information about each location of the railway track.
We implement the train-borne LDV technology on the CTO measurement train of TU Delft. This is a laser head that is pointing a laser downwards to the track surface, so that when the train is moving, the laser sport scans the track and measures its vibration. We have also accelerometers and video cameras to provide supplementary information for the analysis. The non-contact, direct and continuous measurement of the track vibration from a moving train is a very good, very efficient idea, but to make it happen, there are also many challenges. The first one is the so-called speckle noise. It originates from the scanning of the laser sport on top of a rough surface. So basically because all the surface of the track structures are rough, so we have a lot of noise in the LDV signal. Speckle noise is super random, super non-linear, and it changes with respect to the speed of the train. We have been developing algorithm within this project to try to mitigate speckle noise and preserving the vibration of the track. And the next challenge following the mitigation of speckle noise is to integrate the signal, to extract useful information from the signal so that we can assess the dynamic properties of the railway tracks.
I'm very enthusiastic about what we are doing with LDV, also in the Europe's Rail project. I know it's still a lot of development, but we can capture much better the dynamic properties of the track and all the different components of the track. I'm getting more excited by the fact that within the Europe's Rail project IM4Rail, you are now really testing it on this CTO train. We should actually try this technique and demonstrate it in other countries as well. The iron ore line of Sweden, we did it with ABA, so why can't we do it with LDV? So that should be a next step in my perspective. We invest together, we learn from each other, and we'll hopefully come to the standardized good solutions for the, in this case, infrastructure monitoring.